Yeah. So thank you everyone. Thank you everyone for coming to today's talk. So today we have Samantha presenting her paper High Accuracy Calorimetric Measurements and Modeling of Ceramic Capacitor Losses under Large Ripple Operation. Samantha is a PhD candidate at University of California at Berkeley. Please go ahead, Samantha. Please go ahead.
Awesome. Thank you. And thank you everyone for being here, I guess, tonight or this morning. I'm really excited to present this work. We've been doing a lot of work on multi-layer ceramic capacitors and how to characterize them under what we call more realistic operating conditions. So I'm going to start off today about explaining why we care about these capacitors. This is going to be a long talk just focusing on one device. So we want to motivate why we think these devices are important and crucial for moving power electronics forward. And then I'm going to talk a lot about the calorimetric based characterization that we performed. So it's a very tedious measurement, and we'll go into all of those details and about why we did that measurement. Then we'll go through a lot of data, and we'll try and pull some trends from that data in order to make a model that the everyday designer can use in order to better design with these multi-layer ceramic capacitors. So why capacitors? This is a plot made in 2015 by surveying all of the available capacitors and inductors for power in DigiKey. So on the bottom, you see the voltage rating of the capacitor and the energy density. The energy density is calculated as 1/2 CV squared and then divided by the volume. And then we have the same thing for inductors using the current rating, and again, 1/2 Li squared to depict the energy density of the inductor. And what you can see just from looking at this plot is that capacitors have the ability to be over 1,000 times more energy dense. And you can look at the same comparison in another way. This is an inductor and a capacitor, which have the capability to store the same amount of energy. So just looking at this, it tells us that if we are able to use more capacitors than inductors, we're going to be able to have a more dense and more powerful converter. And so here are two examples of some converters that do just that. Here is a inverter developed for NASA's More Electric Aircraft project. It's a 1 kilovolt bus DC AC output. It's a 10-level flying capacitor, multi-level switched capacitor topology. And it has a peak efficiency of 98.6% and a power density of 26.7 kilowatts per kilogram. So it's an extremely dense converter. And the reason it's able to be this dense and have this high efficiency is because of these capacitors. So some of the capacitors are covered up because of these heat sinks. But if you look here, you can see this box here. These are the MLCCs, and there are 8 of them per level, and there's 10 levels. So there's quite a bit of these capacitors on this board. And this is a case of a higher voltage system, switched capacitor system that primarily uses these capacitors. But here's a lower voltage system that also uses capacitors as the primary energy storage element. This is a resonant switched capacitor 48 to 8 volt topology with a peak efficiency of 98.5% and a power density of 2.23 kilowatts per inch cubed. So I specifically wanted to point out this one because Rose is going to give the talk next week, and this is the work that she's been doing, and it's super awesome. So I recommend that you tune in. So going back to this 10-level FCML, this is really where this work spawned from. So I want to explain kind of how we got into looking into these losses. So this FCML, before we designed it, we modeled it. We have a simple MATLAB script that we try and take into consideration conduction losses, switching losses, inductor losses. And doing this, what we found is our losses should be at the top of this yellow curve here. What we're finding when we did experimental data is that our losses were actually at this red curve. Now that difference ends up being peak efficiency of what we modeled was 99.1%. What we're actually getting is 98.6%. Well, that might seem like a small difference. That few percentage points makes a huge difference in the amount of heat dissipated and allows us to push to higher power levels. So we're interested in understanding why our loss model isn't as accurate as we had thought. Now, there were 2 main losses that we wanted to investigate once we looked into this. The first one is dynamic RDS-on. And since this was a few years ago, and since then there's been a lot of literature about this dynamic RDS-on effect in GaN devices. So I won't go into any details about that, but we did pursue that as well. But the project I undertook was, what about the capacitor losses? Just sheer numbers, you can see that there's way more capacitors on this board than maybe a typical board. And so their losses are going to add up, especially because we have about 6 amps RMS flowing through them. Now I'm going to pause for a second. We're going to talk about what is a multi-layer ceramic capacitor. So it's just a special kind of capacitor that is made up of interwoven electrodes. They do this because you're effectively decreasing the distance between electrodes while also increasing the area of the plates. So if you remember, capacitance is permittivity times area over distance. And so by doing this, you're able to have a very high capacitance in a small package. There are 2 types of MLCCs that are primarily used in power electronics. There's class 1, which are made up of a paraelectric material, which is stable over operating conditions. So they won't derate with bias, which we'll talk about here in a moment. So they're a nice choice if you want a stable capacitor. But class 2 MLCCs are made up of this ferroelectric material, usually barium titanate, which allows for extremely dense storage. So they have a high permittivity. And again, back to that C equals permittivity times A over D. That high permittivity allows for a really large amount of capacitance in a small package, but they have this interesting effect where their dipoles will change depending on the environment. So we'll talk about the DC bias and some other effects which can change how this MLCC operates. For the purposes of this talk, we're going to talk about a simplified MLCC model. You can look more into how there's more complex models, and there's a lot of different things going on in this system, especially because of the interwoven plates. But it can be boiled down to an ideal capacitor, an equivalent series resistance, and an equivalent series inductance. This equivalent series resistance is what's going to contribute to the real losses of this capacitor. So we can calculate the losses as I squared R.
And
so when you
just one question, are MLCC
yes.
DC or AC capacitors? Can we use them as film capacitors?
AC capacitors. You can use them with a DC bias, though.
Okay.
Yeah. We'll talk about that some more.
Okay. So they have a polarity then?
No, they don't have a polarity. No.
So you can use them in AC applications, right? Okay.
Yes. Yeah. So MLCC losses. So if you go, you've decided you want to use one of these class 2 MLCCs in your design. You open up the data sheet. You will definitely find a curve that looks like this. So this is the capacitance change with DC voltage bias. So as the DC voltage increases, your capacitance is going to decrease. And you can see it's quite substantial. So at full rating, you could be, in the case of this capacitor, only have 17% of your initial capacitance. And so this is a really important effect, and it's well documented in the data sheet. But if you want to know more about the losses, most likely you're not going to find anything on the data sheet. Usually if you reach out to manufacturers, they're really nice and they'll send you a few curves that look like this. So this is the ESR versus frequency. And this is a helpful plot, and even here's a view of the zoomed in ESR versus frequency for the frequencies of which we operate capacitors in a switched capacitor topology. But the problem is this data is only at 0.1 volts RMS, small signal excitation. And this is not at all how we're using these capacitors in the switched capacitor topologies. In fact, we usually have several amps of current running through the capacitors. So they have high current. They have DC bias. So in the FCML converter, each of these capacitors is biased to some VDC over n-1 times whatever level they are. So in the case of this buck FCML, these highest capacitors have, they share up to 1,000 volts across them. In reality, that's built by making 2 series capacitors. So each one has 400 volts across them. And they have high frequency content in the waveform. And that's just a fancy way of saying it's not sinusoidal. So if you look in particular at the current waveform, it has these sharp edges. And we know that these sharp edges impact the losses. We're not quite sure how, but we know it's important. And so to get a better idea of what the losses are, we know we need to be able to characterize the MLCCs under these operating conditions that are more similar to that of switched capacitors. And furthermore, what we want to know is, can we develop a model that can be used by others so that when you go and design these converters, you have a better idea of what your losses will be off the bat. So our motivation is there a way for us to classify these MLCC losses, so the ESR, under all of these operating conditions? You can call this maybe our hypothesis. Our hypothesis is that these 5 conditions are most likely going to affect the MLCC operation. Temperature, frequency, AC amplitude, DC bias, and then excitation shape or harmonics. Now, right away, we can check off temperature and frequency. I showed you a frequency plot given by the manufacturer, and while it is at small signal excitation, we're still going to say that tells us how frequency affects ESR. Temperature, again, usually not given on the data sheet, but you can reach out to the manufacturer. And so this is the case of a TDK capacitor where we were lucky enough to have a good conversation with the manufacturer, and they were able to provide this information, which is how the ESR and temperature are related. So we have temperature and we have frequency, which leaves 3 main questions left in our heads: AC amplitude, DC bias, and excitation shape, or the harmonic content. So the simplest idea is, when I want to do these measurements, I want to go into the lab and I want to hook it up to a power analyzer, take a few measurements, and be done. That seems simple enough. So in the case of the converter that we're specifically targeting, here are some of the measurement specifications. The current through any given leg is 6 amps. The voltage, like I said, varies depending on where the capacitor is in the circuit. But let's take the case of 400 volts and a ripple of 10 volts. That means the amount of transferred power of these capacitors is 2.4 kilowatts. You find that just by taking 6 amps times 400 volts. But what we're trying to measure is actually a very small number within that full transferred power. So we only want to measure probably about 1 watt of loss. We aren't 100% sure what these losses are going to be, but we know that they're not going to be on the order of kilowatts. Using this WT3000, which is the fanciest power analyzer we have in our lab, the best accuracy we can do at 500 kilohertz is plus or minus 10.2 watts, which means we're trying to measure something that's 1 watt plus or minus 10.2 watts. So this is not a feasible method to characterize our MLCCs. And this is not great because that means we need to do a more advanced measurement technique. And we decided to go with a calorimetric measurement. And we'll talk a little bit more about that in a few minutes. But if you're interested in the different possible measurement techniques that we looked at and why we chose calorimetric, I'll have a citation from my master's thesis at the end, and I go into great detail about there are some methods where you can use thermal cameras and all of these different things. So we decided to go with the calorimetric method because our analysis told us it was going to be the most accurate.
Samantha, there are a couple of questions. Do you want to take them now or at the end of the talk?
Yeah, I can take them now. So the first one, why metallic electrodes are non-uniform. So I think maybe it was just my figure. I think they're usually pretty close to uniform within the structure, but I'm not 100% sure. And a lot of the time it's details that the manufacturer won't disclose to you. So we've actually talked about taking one and opening it ourselves, finding a way to saw into it somehow, because we don't actually know what's going on inside the structure. So if capacitance is a function of voltage bias and voltage division is a function of capacitance, how does the series connection of MLCCs work? So that's a great question. So when we model these converters, that's something we have to pay very close attention to. So in the converter shown here, each of these capacitors that you see in this schematic is actually 8 capacitors, 4 in parallel in series with 4 in parallel. So a total of 8 capacitors in a matrix. And because you have your voltage across them split in half, and we can assume that that voltage is going to split evenly. We're actually doing some work into whether or not that's completely true, but usually you can assume the voltage is split evenly between the two series capacitors. And then from there, we usually calculate the capacitance based off of voltage bias using this plot.
Yeah. Nachiketa, does it answer your question? You can unmute and go ahead if you have any other questions. Okay. Okay, I think it answers his question. Yeah.
Okay.
Yeah.
So in order to do these calorimetric measurements, we need to create some kind of electrical test circuit that allows us to measure the losses of the MLCC in this calorimetric setup, but by being able to independently tune all of these variables. So we want an electrical setup that allows us to have high harmonic excitation. So that's that square waveform I was talking about. We don't want it to be sinusoidal. Hundreds of kilohertz frequency. So in the switched capacitor topologies we're targeting, we know that we usually operate in the hundreds of kilohertz range. Large AC excitation. So again, in this converter, we have 6 amps flowing through each capacitor, and then a large DC voltage bias across the capacitors. So this is our 4 things that we want from our electrical test circuit. So I'm going to walk you through how we design this circuit. The first thing is high harmonic content excitation. So we were able to do this. We just made a H-bridge, which was implemented using GaN systems devices. And for now, we'll say we have an ideal current source right here called I-bridge. And if you operate these switches with 50% duty cycle, you can see this nice square waveform that we get here. And this is our device under test, our MLCC here. So first thing is done. We have a high harmonic content excitation. The next thing is we want hundreds of kilohertz frequency. So we want to be able to switch this very fast. This is simple because we chose GaN systems devices. They're able to switch very fast. And so we can just, using a microcontroller, change the frequency of these switches very simply. The next thing is amplitude. So we want to be able to increase and decrease the amplitude of the square waveform in order to understand how that affects the losses of the MLCC. So I said before, we were going to use an ideal current source. So you can imagine if there was an ideal current source, we could just turn the knob on that ideal current source and that would change the amplitude. Now, you can't get an ideal current source. So instead we implement this using a voltage source operating in current limiting mode and a very, very, very large inductor. Just to note that this inductor is so large, it's placed outside the temperature chamber. And so it's far away from the device under test. So by tuning this V bridge and our current limit, we're able to change the amplitude of this AC excitation. And then the next thing is the DC voltage bias. So we want to be able to change the voltage bias of our device under test. And so we do that by adding this voltage source here and a very, very large C bias, which is several orders of magnitude larger than our device under test, so that it just acts as a stiff voltage source. And by doing all of this, we're able to control those factors that we wanted to control. And even nicer is we're able to control all of these things outside of the temperature chamber. So this box here signifies the temperature chamber. So you'll see that we have part of our circuit outside the temperature chamber and part of our circuit inside the temperature chamber. So the reason why we did this is because we really wanted these square waveform. I've talked about that a lot. We think that that is really interesting part of this characterization. And if we have any kind of inductance in the line here, that square waveform is going to start to round. So what we did is we took the H bridge and we actually mounted it in the temperature chamber so it was as close to our device under test as possible. But the rest of our circuit, the AC amplitude knob and the DC bias, all of this is outside of the temperature chamber, which makes it really simple for us to change those independent variables so we can understand how they affect our losses. Here's a little bit more about the calorimetric setup itself. So we use this paper below as a basis for our calorimetric setup. It's a really great paper talking about, they look at calorimetric setup for power converters as a whole. Obviously, we're looking at just one device, but they suggest an oil-based calorimetric method. And so what that means is we take a beaker of mineral oil and we dip our device under test inside of it. And by doing this and using oil, you can use a special scientific grade oil that you know all of the factors and parameters, so you can understand with a degree temperature rise of the oil, how much power is being dissipated in the oil. And so here's our beaker of oil, here's our device under test. It sits on top of a magnetic stirrer, and we do this so that we have equal temperature throughout the oil. And then, like I mentioned on the last slide, we actually have our H-bridge mounted directly on top of the device under test. So you can't see it here, but below this is where we have we actually use large pieces of copper to go to our device under test. And then we have our microcontroller here as well. So this again is mounted directly on the beaker so that we're as close to our device under test as possible. All of this system goes inside this temperature chamber here. You can see, maybe you can't see, but there's a hole on the side of the temperature chamber where you put all of the wires through and then you stop it up. We use the temperature chamber because it helps keep this ambient temperature constant. It's not completely necessary to do these kinds of measurements, but we did find, we originally started these measurements back when we were still at Illinois, and Illinois has a brand new building, and it's one of the fancy buildings that will kick on and off the air conditioning depending on who's in the room. So when we were doing these measurements, what we found is we were able to detect those huge swings in temperature as people were coming in and out of the room. So that's why we ended up going with the temperature chamber. Again, not completely necessary for these measurements, but helpful for us. So this is the temperature chamber. These are our two voltage supplies that allow us to tune the AC amplitude and DC bias. We use a data recording device that goes directly to MATLAB so that we can easily capture all of our data. And we measure the temperature using thermistors. Again, if you're interested, I go into a long discussion in my master's thesis about thermistors versus thermocouples versus the thermal camera. So we use thermistors inside this temperature chamber to measure the ambient temperature, and then we use them inside the oil bath to measure the temperature of the oil.
So, Samantha, I have one question, quick question. Since the capacitor is cylindrical and there is uniform heat distribution all around, we could also use a simple temperature sensor, right? Instead of this setup to measure.
So we looked into that. So the capacitor is actually not cylindrical. It's more of a rectangular shape.
Okay.
And we found that we just couldn't get an accurate enough measurement because it depended on where you would put the temperature sensor.
Yeah.
Now, I think and we'll talk about this maybe at the end, I think if you're trying to do simple measurements just to get an idea of what your losses are going to be, I think that would be more than good enough. I think we just wanted to make this as accurate as possible to develop a model, but I think something like that would be good enough for like a first order effect.
The geometry plays a big role. Yeah.
Yeah. So we measured the temperature using the thermistors. I already talked about this K oil factor. The last big part of a calorimetric measurement is to understand the thermal resistivity of your setup. So pretty much that means is how much heat is escaping from your setup just because it's not thermally isolated enough. And actually not shown here, we actually wrap this in some thermally insulating material to try and increase our thermal resistivity. So we calculate the thermal resistivity of our setup using a calibration method. So we'll do some runs of the setup, but instead of using the MLCC, we use precise resistors. So it's a resistor that we know what it is within 0.1%. And because we know what the resistance is, we know what current we're running through it, we know exactly how much power should be dissipated. And then we measure the temperature over a very long period of time to let it come to steady state, which is what you see here. And that change in temperature allows us to back out what the thermal resistivity of the setup is. I put the citation here from my master's thesis because I keep mentioning, I go into a lot of detail about the accuracy of the setup. It was something that was really important to us, and you'll see throughout the rest of this presentation, there's always error bars on every measurement that we do because we want to show that we put thought into the accuracy because it is quite a tedious system. So we want to show why we put this setup together. Okay, So now we're getting to the exciting part, the actual results. So we tested 5 different capacitors. I want to make it clear that this is not supposed to be a comparison of technologies. If you look at this table, they have a variety of voltage ratings, a variety of capacitance. We more just wanted to get an idea if there was general trends between technologies. So the first 3 capacitors listed here are class 2 MLCCs. They're actually the capacitors that we use most frequently in our lab, but they have a variety of voltage ratings and capacitance. The next one is a Sierra Link capacitor, and Sierra Link is a really exciting new technology. It has an anti-ferroelectric dielectric, so it's actually opposite of the class 2. And so with DC bias, it increases capacitance. So that was kind of one that we wanted to test just because we were curious of what would happen with that one. And then lastly, we wanted to test a class 1 dielectric. And this is the dielectric that I mentioned was stable over operating conditions. And because it's stable, we kind of thought, another hypothesis, if you will, that we would see a stable loss over operating conditions. That made sense to us. And so that's what we were hoping to see. So these were the 5 capacitors we looked into.
And among the 1 microfarad capacitor, which had the smallest footprint, or does that matter?
They're all almost the same footprint. So the Sierra Link is the only one that has a different package. And that is something to note and something we thought about whether that would impact our setup or our losses. The Sierra Link uses I think they're called J leads on the side of the MLCCs. So it is a little bit of a different package. The rest were all a 2220 package.
Because your measurements are so heat sensitive, if their geometry varies, I think that also might have an impact.
Yeah, exactly. And so that's why we wanted to keep it constant, but definitely, and this is something I'll talk about, I think to do like a full comprehensive model, you would have to do the same analysis now with let's say 0805 capacitors and choose all 0805 and do the same thing. So I'm going to talk about some results here. There are many, many, many more plots in our published work, but we'll break it down to just a few of the really important results here. So this first plot is for the first capacitor we showed, the TDK X6S. This is actually the capacitor that we use in the converter pictures that I showed previously. So what we're looking at here is how does DC voltage bias affect the ESR? So for these tests, we kept a constant AC amplitude and then changed the DC voltage bias. And the AC amplitude for these tests was 6 amps RMS, just because, again, we're kind of targeting that one converter in particular. So that's what we used. So if you take a look here, it's a lot of data. So let's focus first on the green dots up here. You'll notice that all of these dots do have error bars, again, because we thought that that was really important to our measurements. So we have 500 kilohertz here. What you can see is with increasing DC voltage bias, we see an increase in ESR. And in fact, the full bias ESR is about 2 times that of the no bias ESR. Now, if we look at the same data for the 250 kilohertz, the red triangles down here, we see the same thing. With increasing DC voltage bias, we see an increase in ESR. And in fact, you see this across all frequencies for all of the class 2 MLCCs we tested, the same trend. It's not always exactly linear. Like you can see here, this isn't a perfect line, but it does seem to have some kind of linear relationship that with increasing DC voltage bias, we have an increased ESR. A few things to point out, maybe some nuances here, is if you look at the specific frequencies we tested, the frequency relationship is nonlinear. So what I mean by that is if it were linear, I would expect 75 kilohertz to have the lowest loss, and then the lines would increase like that. And that's not true. In fact, you can see that 250 kilohertz is the lowest and 500 kilohertz is the highest. This actually is related to this frequency relationship. If you remember that curve I showed before, it's not a linear curve, it's curved. And in fact, this is why we're really interested about the high harmonic content, because if you look at, let's say 500 kilohertz, the third harmonic, since this is a square waveform, we have the third harmonic, and the third harmonic falls past the self-resonance point of the MLCC. So that's why we think that's an interesting effect as well. But just looking at the results here, we see that there's a strong relationship between DC bias and ESR. Next, I'm
what
going to
do
talk about
these
the,
upper and lower bounds signify, Samantha? If I look at
so that's the accuracy of our method. So again, in that master's thesis, I go through what is the expected error due to the thermistors, what is the expected error due to our measurement technique, and all of these different things, and that tells us what our bounds are.
Okay.
So yeah, and you can see that under certain operating conditions, the accuracy is wider range.
Okay.
Okay, so let's talk about the Sierra Link. This was the one we thought would be interesting because it has that different dielectric material. And what we find is the same trend. With increasing DC voltage bias, we see increasing ESR. And so this is really interesting because even with a different dielectric, we see the same trend. Now, kind of a check on ourselves, what we did was we tested the class 1 MLCC to see if we had the same increased DC voltage bias and ESR. If you look at this data, there's not an increase that we see with the class 2 or the Sierra Link capacitors. There is some variation, and this could definitely be studied further, but we know that it's not the same relationship that we see with the class 2 or the Sierra Link. So this checked with what we anticipated we would find with these capacitors. We wanted to do one more sanity check before moving on, because this was quite important data, right? We were finding that the ESR was 2 times what it was at 0 volts. So we wanted to check that. Previously, I said we couldn't do electrical measurements because of the accuracy of an electrical measurement at the frequencies we wanted to test. But we can do an electrical measurement if we test at much lower frequencies. So I guess this still isn't low frequencies for most people, but for the switched cap world, 500 hertz is pretty slow. So we did these electrical measurements, and you can see that the accuracy still isn't great. We have pretty large error bars, but we did the electrical measurement using this technique shown here. So it's going to be sinusoidal, and it's going to be lower frequency. So this isn't exactly what we're looking for, but we just wanted to see if there was the same trend that we were finding. And sure enough, if you look at the data shown here, at 100 volts, we have about 0.25 ohms ESR, and at 350, it's about 0.52. So we are seeing that same almost doubling effect of ESR, even at the low frequencies with a completely different setup, sinusoidal and everything. So that confirms to us that this is a real effect that we can definitely quantify, that ESR increases with DC bias. The next thing we studied was AC amplitude. So now we kept the DC bias constant, but we changed the AC amplitude of our waveform. And we varied it over 2 amps to 5 amps. I purposefully have left the y-axis here the same as the y-axis for the plot I showed you for DC bias. This is to show you that AC amplitude has a much less effect on losses than the DC bias. It does, again, similar to the class 1 MLCCs, there is some variation among RC, among current amplitude, but it's not significant in the same way the DC bias effect is. And so the next thing we're going to talk about is a model, and the first order model we think can really just focus on DC bias because this AC amplitude doesn't have as large of an effect. So I'm going to pause here and remind us why we're interested in all this data. So taking a look again at this 9-level FCML, which is the converter that this work was originally created for. So looking at our 3 class 2 MLCCs, we see at 400 volts, 125 kilohertz, which is the operation of most of these levels in the FCML, our ESR increases by 200% or more at full bias. And so if we look at our original loss model, what we actually found is that we were modeling our capacitor losses at half of what they should be. So we were off by a factor of 2, which really shows that this is quite a big effect that we're seeing. And so we don't expect everyone to go out, get a temperature chamber, get a beaker of oil and do these measurements. Like I mentioned, it's quite tedious. Each of those data points I showed you takes several hours and even more time because you have to let the oil come to ambient in between each run. And so we don't expect people to do these tests. What we want is to develop a model that can be used by everyone so that no one ever has to do these tests again. So our model, we wanted three things from it. We want it to be accurate. This is the most obvious. We think it should match the data that we collected in the lab. Complexity, we want it to be simple. So you have tools like Plex and LTSpice and MATLAB, and we want you to be able to just take this model and plug it into your existing modeling software so it's not difficult to implement. And lastly, and probably most importantly, is effort. So we don't think that the average designer should have to go and do all of this data. We think that there should be minimum extra steps required for using this model. And in fact, in an ideal world, we think that the manufacturer should provide all of the details for this model on their data sheet. So these are the three metrics of which I will describe three different models that you could potentially use. These are the three simplest models we've come up with. We have some interesting ideas that we haven't published yet about some very complex models. But these are the three simplest because I think that's the most useful for people now. First one is the constant ESR model. This would be what the model would look like if you just took the small signal data provided by the manufacturer. So for the case of this plot here at 125 kilohertz, you just looked for the small signal excitation, and it's this red-ish dotted line here, and you just used this value. So you ignored the effect that we found. So obviously the accuracy is quite low for this model, especially at high bias. But complexity-wise, it's the simplest model possible. All you need to do is plug one number into your model. Effort, again, very little effort. Maybe the biggest effort might be that you might need to reach out to the manufacturer and ask them for the small signal data. The next model that we thought of, and maybe y'all had the same thoughts as us, is the capacitance of class 2 MLCCs goes down, and we're seeing the ESR goes up. So maybe there's something to do with the time constant. So we thought maybe the time constant stays constant, and as R goes up, C goes down. And so this is our constant RC model, as we call it. And as you can see here, the data fits very well at low DC bias and overshoots by quite a bit at high DC bias. So accuracy-wise, really good at low bias, not so great at high bias. Complexity, pretty high, because you're going to have to take the capacitance derating curve provided by the manufacturer. You're going to have to digitize it somehow, because usually they don't give you the Excel data for that. So you're going to have to figure out how to digitize it. And then you're going to have to import that into your model. And then you're going to have to go from there. So it's quite a bit of complexity. Effort, though, 0 additional data points. So we're not asking you to take any more data points. It would be just what's included on the manufacturer's data sheet. The last one is the linear model. So this is probably the most intuitive. The data I showed you follows a semi-linear trend. And so if we just use the fact that it's linear, we can estimate what the losses would be. And so in this linear model, we tried a few different things. You can try using the small signal as your 0 volts bias, and then taking one additional data point from there, because you only need 2 data points to make a line, right? This is shown for using the data at 0 volts and 100 volts that we calculated, that we measured ourselves. And then this is the line developed using those 2 points. Overall, the accuracy is the best, right? It looks like it fits. Complexity, you just need to model a linear approximation, which in most modeling softwares is quite simple. Effort, though, you need to take 1 additional data point. And this is something we're looking into now, is what is the minimum effort that would be needed to use this? So a lot of methods that we've talked about, you know, even brought up earlier today, is what if we just put a temperature sensor on top of the MLCC? Would that get us an accurate enough, just 1 data point so that we can make this line? Or using a impedance analyzer. Sometimes you can have a bias with an impedance analyzer up to maybe 20 volts. So would that be enough to get us 1 extra point? So this is what we're looking into now, because again, we think this is the best model, but we don't want people to have to go take more measurements. So we're trying to figure out what is the minimum amount of work needed for people to use this model. And here's just a summary of the different models. So you can see constant ESR, not that great for accuracy, but super easy to use and implement. And so you can see the constant ESR loss or error here, and you can see that it gets pretty large at higher voltage biases. Then you have the constant RC model. Not that difficult effort-wise, but you can see there is a large amount of loss at this DC voltage bias point. And then lastly, the linear model, which as we discussed, has very low error across the board, but requires additional effort. You can even imagine maybe there's some combination of these models that is going to be the easiest approach. For example, you could use the RC model for lower voltage bias, and then use the linear model for higher voltage biases. In fact, sometimes manufacturers or designers will purposefully use these class 2 MLCCs at lower voltage points because of their capacitor derating. So if you're doing that, then you could easily use this constant RC model and be accurate over that narrow range. So in conclusion, I hope that I've made clear to you that right now, data sheets don't provide the loss parameters that we need for MLCCs, particularly in hybrid switched capacitor topologies. Also, I've shown that DC bias has a large impact on the ESR of class 2 MLCCs. So we can see up to a 200% increase at full bias, which is a huge difference. I've shown a few different models, but hopefully convinced you that linear models are the most accurate, but they require additional effort from the designer. The one thing I haven't talked about is harmonic content. I mentioned that we specifically designed around the square waveform for the higher order harmonic content, but that's something that we're still looking into. So the idea eventually would be that this would need to be some kind of test setup where maybe you would start with a sinusoidal waveform and then have harmonic injection for the third and the fifth and the seventh, and see how that affects the losses. And that would give a more comprehensive loss model to also understand how the harmonic components affect losses. Lastly, I want to acknowledge this work was paid for by the NASA Fixed Wing program. That's why I kept referencing that More Electric Aircraft project, and also the US Department of Energy through the Electric Drives Technologies Consortium. That's it, and I will now start taking questions.
Very good, Samantha. Very good presentation. Incredibly detailed. Could you please go to your setup? I just had one question regarding the setup equivalent circuit. Yeah, maybe.
This one?
Yeah. So what I understood was this is like a scaled up version of a network analyzer where your perturbation is higher. Your amplitude of the perturbation is higher. So can this be used to test even active devices like batteries? Should be possible, right?
Yeah, and actually, yeah, that was the feedback I got the first time I presented some of this work at a much earlier stage. I did have someone who was interested in battery technology say that this would be an interesting technique. I don't know a ton about batteries, but I think that it is possible that you could test it similarly.
Because that is the problem that I face, because the perturbation in normal cases is like, let's say you can consider it as 0 volt. Then you're shorting the battery. So you need to have a source which has a ripple over and above 12 volts or 24 volts. So that is a pretty high power converter. Good.
Yeah. So I think that'd be effective.
Yeah. So we'll go to the audience. Nachiketa had some more question. He had a follow-up. Nachiketa, can you unmute yourself? Let me see whether you can unmute yourself. Okay.
Hello, Janmejay, are you able to hear me?
Yeah. We can hear you. Please go ahead. Nachiketa.
Yeah, Samantha, thank you for your presentation. So I had a follow-up question on the series voltage division that you explained. So let us say during practical manufacturing tolerances or any practical
Nachiketa,
errors.
we lost you for a second. Can you just repeat the last part?
Yeah, I am kind of on a Yeah, I am kind of on a low bandwidth connection, so I would prefer if
Yeah.
Samantha reads
Yeah,
my
so
question.
he's asked, there is a small mismatch between voltage sharing of series connected caps during startup. How are we sure that the voltage sharing error does not increase as the DC source voltage increases? Yeah.
Okay, that is a really great question, mostly because we're actually looking at it right now on a different converter. So I don't have an answer for you right now, but I will say that something we're looking at is we have a flying capacitor multi-level inverter, or it's a DC-DC actually for this specific one. And we're looking at the startup for that converter, and we're doing some tests of you can put two resistors in series with those capacitors in order to make sure that they're balanced. So we're doing some testing of whether that affects our results and if we do have inherent balancing or not. So I think that's a great question. And we obviously had the same question. So hopefully we'll have some results to share eventually.
Yeah, he has one more sub question. Are you using some passive arrangement to ensure equal voltage division? How do you maintain equal voltage division?
So not in this converter and not in this test setup. So in this test setup, we don't actually have capacitors in series. We're using two capacitors in parallel and then dividing the current through them and the losses through them. But for this converter that you see here, we aren't using any kind of passive elements to ensure balancing between series capacitors. We have, again, briefly looked into it, and there's some disagreement within our own group of whether or not that matters. So that's what we're looking into right now.
Yeah, and in this picture, he has one more question, but I had a question in this picture. They have heat sinks for capacitors here.
So the heat sinks are for the EPC devices.
Okay.
You can barely see the EPC device because it's so much smaller than the capacitors. These heat sinks are actually milled so that they have a notch that goes down and just touches the EPC. So these modular heat sinks, I think I have the citation for this paper somewhere. We go a lot into how we design those heat sinks. They're quite difficult to implement and to actually get to fit to the EPC device.
Yeah, very interesting. Nachiketa has one more question. What is the package of capacitor chosen for testing? What was the package?
Yeah, so it was a 2220 package. And we just chose that because, again, this work was funded by the same work as this converter. And so these are the capacitors that we wanted to use for this converter. So I think, you know, with any kind of modeling, you always want more data. So if we had a ton of more time, I think we would do the same testing on a round of 0805 and 0603 and try a bunch of different package sizes to confirm that that doesn't play a role, or maybe it does. I imagine that there would be some amount of at least additional ESL because of the type of termination, but it's not clear what the ESR would do under those circumstances. So I think that's a great question and something we'll look into.
One more question. The bias characteristics of the MLCC are highly affected by the package size. They're correct, right? This statement is correct. Is that
I think, you know, I haven't come to that conclusion independently, but if you do look at the different data sheets for the different packages, the derating does change. So I think that would be a valid assumption that that does impact, you know, the type of derating curve you see.
So he asked, the smaller the package size, steeper is the dependency as far as he knows.
Yeah, I would have to think about it a little bit more, but I think that's true. But they still have a pretty steep curve as well. But yeah, I think that would be another great thing to look into is how does this differ under different voltage biases?
And your studies focused on MLCC. Is the same true for, let's say, Maxim ultracapacitor, other ultracapacitors as well?
So it's going to be a little bit different, at least. We thought about looking into that as well, but we haven't. Obviously, we've just focused on MLCCs. We have presented this work, or a version of this work, at APEC does a capacitor workshop the day before APEC, and that has a lot of capacitor manufacturers there, and they said that they were seeing some similar effects in different technologies of capacitors, but it hasn't been tested or verified. It was more of just conversation that they thought it was applicable to other technologies.
Got it. Got it. And one last question, the same person, about the metallic electrodes are non-uniform. Any comment on that?
Yeah, I think I already answered that one actually. I think that I think they are uniform, but I'm actually not sure. So I think that's something would be interesting if the manufacturer would let us know, or if we could cut one open ourselves.
Good. Yeah, I think that's it, Samantha. Very good presentation. Thank you for answering all the questions. And which groups around the world are they working on this while you are doing your literature review? Did you see anybody?
Yeah, so in particular, ETH actually just a few months ago came out with a paper that is really fantastic, and they do some measurements at lower frequencies. So they're specifically interested in buffering applications. So they're looking at 50 to 120 hertz. And they have suggested a model that's similar to Steinman's equations for inductors, but for capacitors. So that's really exciting, and something I'm hoping to do looking forward is their work focused on one capacitor in particular. So I'm hoping, since I have this data from a lot of different capacitors, I can attempt to use their model that they suggested and verify it, and work with them to see if that model that they suggested at low frequencies also holds at high frequencies.
Yeah. And since the experiment is so tedious, is there a way to do it parallelly, or you have to do one at a time for hours? And
I think you could do them in parallel if you had the equipment to do that. We just didn't in our lab. We did start to do certain things to speed it up, like we had multiple beakers full of oil so that we didn't have to wait for the beaker to come down to ambient before doing our next run. And that was really helpful because there's a lot of thermal mass in that oil, so it takes several hours to come back to ambient. So that speeds up the process. There's also some, if we look at the calibration, so most of our data, we're looking at this linear part, and we're able to tell the losses just from that. So most tests were done within 100 minutes. So this part of the data. And in theory, if you feel confident about this data, again, it's a line, so you could stop it much earlier in time. And so in my master's thesis, which is cited here, I go through how long do we need to make each test in order to get accurate data, because the faster the test, the more tests we can do. But we found there was a trade-off in accuracy.
Good. And during your master's, Samantha, when you defended your master's thesis, what were the questions asked by the committee, or which were the most that you can remember?
I actually have an answer to one of them. This is the question I get asked the most, which is, you're measuring the ESR based off of the temperature change. But I started off by saying the ESR changes with temperature. So, you know, is there a second order effect there? And so what we did to confirm that we weren't measuring just the ESR change due to temperature, which first of all is the opposite relationship of what we're seeing. What we did was we took the temperature data and looked at just the operating region that we're looking at. So usually our tests were around 23 degrees C, and we saw at most maybe 8 degrees temperature rise. So you can see that there's only a 2% change in ESR, whereas we're seeing a 200% change in ESR. And so we, using error and accuracy, determined that that was not an effect that we were seeing.
Okay. Very interesting. Okay, good. And for this paper, what were the reviewer comments?
Actually, for this paper, I don't think I got a lot of reviewer comments that were questioning. I think one of the questions was this about the temperature change. And then I guess in particular, why the frequency relationship is not linear. And we've talked about how, is there a way to just look at the small signal frequency data and then do a, look at where the third order harmonic is. So looking at this data, we can look at 500 kilohertz and we know the third order harmonic is going to be, I don't know, somewhere over here. So could we do some kind of summation of harmonics? We decided that it wouldn't work mathematically. So we're looking into that, but that's another question that we get frequently. We also get just a lot of questions about why certain technologies have higher losses or less losses. And that's not something we know because again, the manufacturer doesn't let us in on all of their secrets. So we just have to kind of take everything at face value of what we measure.
Yeah. Very good, Samantha. Very good seeing such very relevant work and very good analysis. Hope to see more work from you in the future. So are you planning to extend this or are you working on something else for your PhD?
I'm working on something else now. So now I'm working primarily on high voltage DC-DC converters. But we're hoping that we can at least do a little bit more on this, maybe with some help of some undergrads or new grad students.
Good. There are a couple of PhD students in the audience as well. When picking GaN devices, do you have any words of caution or advice for wideband devices?
Yeah. So we mainly work with GaN devices only. So, well, I've only worked with GaN devices. Other people in our group, like Rose, will talk about silicon next week. So with the GaN devices, I've worked with both EPC and GaN systems. I think it just depends on what you're looking for. So we've worked on both space applications and air applications. Both of those prefer the packaged part. So that's why GaN systems is a little bit better. We in particular focus on the GaN systems topside devices because they're nice for cooling. So another design I'm working on is a dual-sided design. So you have GaNs on both sides. So by using that topside cooled part, you can heat sink on both sides, which is very nice. I will say, I think the failure rate among all of the GaN devices is equal from my experience. I've seen both not function correctly. I will say EPC has the problem with maybe cracking of the device, which is a little bit difficult to see. And then it's a little too late if you've cracked the device and you try and run the converter. Good. So yeah, I think it just depends on your application, which one's better.
Yeah, working with GaN is a challenge. Thank you very much, Samantha, for sharing, presenting this paper. We greatly appreciate it. Thank you for your time.
Thank you. Have a good day.
You too. Thanks.